we need to look at equations of lines in one dimension, and then see how do we generalize the notion of an equation of line in one dimension to an equation of line in several dimensions. So let's start off with what we know. How many ways do you know to write a line in one dimension, or sorry, in the plane? What are the ways to write lines? Equations of lines. What are the different forms? Yes?
Point slope form.
Point slope. My personal favorite. I give you a point, say x naught, y naught. I give you a slope, m. Here's x naught, y naught. I go over 1 unit. I go up m units. And I use that to get the equation of a line. And it's y minus y naught is m x minus x naught. We can rewrite this as y is y naught plus m x minus x naught. And it's rewriting it like this that gives us an idea of why it's so important in calculus. The whole point of calculus is to take complicated functions and replace them with simpler ones. Okay? So if I give you some strange function like this, I can replace it locally with a straight line, with a tangent line. And we have ways to find this in Calc 1. And the idea is straight lines are easy to work with, complicated functions are not. So imagine you're driving from Boston to Baltimore, and you want to figure out what is your instantaneous speed at some point in your trip. Is it a good idea to use the total time traveled and the total distance elapsed to calculate your average, your instantaneous speed? Okay, why not?
Well, it's a much longer, more tedious equation to figure it out.
Well, no, I mean, I know it took me 8 hours. I traveled so many miles.
And your speed's also variable throughout.
Your speed is variable.
At that one
Your
time.
speed is very variable. You could be going through a city. You could be on a highway. You could be on a small connecting road. There could be a traffic accident. If you go over a large period, there's a lot of variation. If I look at a 20-second window, my speed should not change too much in a 20-second window. Maybe there's an accident. Maybe I see a cop up ahead. Something, that all of a sudden causes me to drastically change my trajectory. But for the most part, over a 20-second window, I'm not going to have a significant change in speed. So if I look at time traveled, and if I look at distance traveled, that ratio is going to be a good approximation. If you want a better approximation, what could you do? Yes?
Shorten the time.
Shorten the time. If you shorten it too much, we now start to have issues that maybe we're not able to measure things significantly well. You try to measure things in 1/1000th of a second, I don't really trust the equipment on my Toyota. Okay? I wouldn't trust it on a Subaru or Ford or anything like that for people who are watching. Okay? It's just a question of how accurately can you measure things. The larger the window, the smaller the errors in the measurement, but the more variation that's going to go on. So this is why we like calculus. This is why we like equations of lines. And if you think about calculus, think of this as f of x is f of x naught plus f prime of x naught, x minus x naught, and we'll put it in approximation. It's almost equal to this. And the way you view this is f of x is where you are, f of x naught is where you start, this is your instantaneous speed, this is the time elapsed. And so as long as x is close to x naught, the straight line is a really good approximation. Think about other equations for lines. We can also give you point. So I can give you 2 points. And if I give you 2 points, you can find the line. Well, if I have 2 points, I can calculate the slope. Once I know the slope, I can use point slope. Mathematicians are lazy. It's a good thing. Okay? We reduce things to things we already know how to do. So if I give you 2 points, it's not a problem. Okay, what else could I do? The last is slope intercept. So I could give you, here's where I hit the y-axis, here's my slope. And this will be y is mx plus b. So depending on how you're given information, different forms of the line are more convenient. Okay? What I want to do now is I want to look at how can we write a line in 2, 3, 4, 5, 6-dimensional space. Well, we've already done lines in 2-dimensional space. Lines in 1-dimensional space is pretty boring. that one-dimensional space is your line. Two-dimensional space is what we're used to. The question is, how do we generalize what we've done in the plane to three-dimensional space? Well, let's think about what a line is going to mean. So, general equation of a line. So the input is a point P and a direction V. So line is all Q such that Q minus P is parallel to V. So if you want to think about what's going on, here's the origin, here's my vector P, here's the direction V, and I want the line going through P in the direction V, right? That's going to be the line going through P in the direction V. So if you think about it, if I take a point over here, Q minus P is going to be this vector over here. It's in the same direction as V. It's parallel to V. It's a multiple of V. If I took another point over here, Q minus P is still going to be a multiple of V. If I went backwards, is it still a multiple of V? Yes, it's now a negative multiple. So we say this and its opposite are in the same direction. We're a little bit, sloppy at times. Okay, V and negative V, they're both in the same direction, really. One is just going forward 1 unit, one is going backwards minus 1 unit. So one is going backwards 1 unit, or forwards negative 1 unit. What if I took Q to be up over here? Would that still be on the line? Would that be on the line? Yes?
If you stop on the line, but if you overshoot it like that.
If I overshoot to here,
No.
no, because now Q minus P is no longer in the direction of V. How many dimensions is a line? What's the dimension of this object? It's a one-dimensional object. So I should be able to specify where I am with one parameter. So the equation of the line can be written as Q is P plus T times V. Start at some point P and move T units in the direction of V, where T is some real number. So whenever you see notation, you should always ask, why did we choose this notation? Why are we using the letter T? I mean, it's a nice letter, it's easy to draw. I like that. But why are we using the letter T? Yes?
It reminds you of time.
It reminds you of time. So think of it as, at time t equals 0, the easiest time to analyze, you're at the point P. At t equals 1, you've moved one multiple of V down. At t equals 2, you've moved two multiples of V down. At t equals minus 1, you're V away from the starting point P. So we like to use T to really highlight the fact that it's a study of time. I could write this another way. I could expand this out. I could say Q equals maybe XYZ, and then I would get XYZ is maybe the point P1, P2, P3, plus T times V1, V2, V3. So if I write it like this, this is another way of writing the equation of the line. And I can unfold things. I can get X is P1 plus TV1, Y is P2 plus TV2, Z is P3 plus TV3. And if I do it like this, it's not immediately clear that this is the equation of a line. I've got a lot of variables going on. But my point P is fixed, my point V is fixed. Once I specify T, do I know X, Y, and Z? Yes. There's only one unknown. Well, if you want, there's 4 unknowns, but really, once you specify T, then X, Y, and Z all fall out. Conversely, if I specify X, do I know Y and Z? Yeah, if I know X, I can solve for T, and now that I know T, I can find Y and Z. Once I have one piece of input, if I'm on a line, I have no more freedom. I know exactly where I am. Does this look like the equation of the line you grew up with? Not even close, right? So let's try to recast what you've seen before, and let's look at it in a new way and see what's going on. So what are the two inputs we need here to get the equation of a line?
Point in a direction.
A point and a direction. When you go back to point slope, the greatest of the three ways to write a line, do we have a point and a direction? So a direction is a vector. Do we have a direction, yes or no?
This slope is like a unit vector.
The slope is, okay, I wouldn't use the word unit. The slope is kind of like a vector. So what's the vector associated to the slope? So let's say, for example, I give you something like this. Let's make it steeper. So the slope is 3. Yes?
So is this the 1m?
Yeah, it's like 1m. So if the slope is 3, I go over 1 unit, I go up 3 units. There's a hidden direction. Your teachers in algebra years ago could have introduced you to vectors. They had good reasons not to. Okay? But when we're going into higher dimensions, we really do want this language. In the plane, we can get by without it. But there's a hidden vector. The vector is v is 1, 3. Or more generally, 1m. What's the one slope that could cause issues? Yes?
Vertical line?
Vertical line. I go over 1 unit, I jump up infinitely high. Right? It's not just because I'm on drugs and I'm not feeling well. Even in my prime, I could not jump up infinitely high. Okay? Why can't I do that? Slope's undefined. Well, if you think about it, it's not so bad that things are breaking down there because my slope is undefined. I have to be a little bit more careful. But you'll see that this notation is actually much better. In this notation, I can just have my vector v going straight up. 1, 0 makes perfect sense. Or 0, 1, because I want 0, 1, going straight up. That's well defined. So this notation allows you to write things down in a much nicer way. What I want to do now is I want to go through and I want to do an example. And I want to look at an equation and see that the equation of the line reduces to what we have seen before for the equation of a line in a plane. So we're going to calculate the equation of a line using all this machinery, and we will see that it equals what we've done before. All right. So let's take, for example, P is going to be P1, P2. We'll do X naught, Y naught. X naught, Y naught. And we'll do M equals 3. So the old way is going to be Y equals Y naught plus 3 X minus X naught. That's the old way of writing down the equation of a line. The new way is Q equals P plus TV. So for us, it's XY is going to be X naught Y naught plus T times the vector 1, 3. Because since M is 3, we go over 1, we go up 3. And that's going to be the direction. Alright, so if we open this up, what do we get? We get X equals X naught plus T, Y equals Y naught plus 3T. 2 equations. Alright. What class would be really nice to know right now?
Linear.
Yeah, exactly. When in doubt, if I ever ask this question, 98% of the time the answer will be linear algebra. We're looking at systems of linear equations. This is what linear algebra is designed to study. Okay? Let's try to think of how we could rework this. Well, we've got T here, we've got T here. we can eliminate the t variable. There are two ways to do this. We can solve for t in both. T equals blah, t equals blah prime, blah equals blah prime, and solve like that. The other thing we could do is we could multiply the first equation by 3. So however you want to do it is fine. 3x equals 3x naught plus 3t. Y equals y naught plus 3t. Subtract, and we get y minus 3x equals y naught minus 3x naught. And then just bringing the 3x over to the other side, we get y equals y naught plus 3x minus x naught, which is exactly what we had before. Right? So this is a way to see that what you've studied in the past is actually the same as what we're doing now. I've only done it for the very special situation where I have a slope of 3. The argument would follow in more general. I just wanted to use specific numbers. But, in a general proof, you would replace the 3's with 1's. Alright, so if you look at what's going on here, once you specify t, you can find x, you can find y. So there's really only one free dimension. Okay. Any questions on what we've done so far about lines? So we've talked about the standard definition, we've talked about multiple ways of writing equations of lines, we've talked about how to express the standard definition of a line as there's a hidden vector, it's a hidden direction. And a line is basically a base point plus some multiple of a direction vector. And you can expand it out in terms of components, or you can keep it in a more compact vector notation. If you're working in a 2014 dimensional space, you really don't want to write everything down. You want compact notation like this. Okay? It's extremely useful, it's extremely powerful. Okay. Any other questions about lines? So let's just do one last example. So I give you the point 1, 2, 3 and the direction 2, 4, 6. This is a little bit too straight. 12, 41, 36. Right. And I just don't want the point to be in the same direction as the line, as the vector direction. It looks a little bit too generic. So what is the equation of the line? The equation of line is Q is equal to P plus T times V. Or X, Y, Z is 1, 2, 3 plus T times 12, 41, 36. Or if you want, X, Y, Z is 1 plus 12T, 2 plus 41T, 3 plus 36T. Alright, so that would be how we would find the equation of a line given a point and a direction. If I give you 2 points on the line, what could you find if I give you 2 points on the line? Yes? The vector of direction. So there's the generalization of the point. If I give you 2 points, you find the direction. Now that you have the direction, now you can do point slope. Okay? So really, all you have to do is remember how to do point slope, and you're golden. Okay. So now we finished studying lines. What should we study next? There are 2 natural generalizations. What do you think the 2 generalizations would be? What are the 2 different things we can study?
Curvy lines or planes?
Curvy lines or planes, excellent. Right? So curvy lines are fascinating. You can study the motion of the planets about the sun, the motion of a fly ball. Lots of wonderful things to study. Or we can study planes. We're going to study planes next. Why are we going to study planes? Sorry? They're similar. So where do we use lines in calculus? We use lines to approximate functions. Where do you think we're going to use planes?
Approximate families of functions?
Not families of functions. Yes?
To approximate 3D shapes?
To approximate 3D shapes, functions of several variables. If I give you a function of 2 variables and I plot it, about each point x, y in the plane, I'm going to go up a certain height. I'll get this kind of surface in space. So I apologize for whose homework this is. So take some homework like this, I fold it a little bit like this. I've got some three-dimensional shape. And I can now try to approximate it with a line if I just want to move in one direction. But better is to try to approximate it with a plane. And the idea is, just as a line does a great job of approximating a function, a plane will do a great job of approximating a function of several variables. Will the plane be a good approximation everywhere? No. But hopefully, if you stay close to your anchor point, it'll be a good approximation. Now, when I did the equation of a line, I started off with, here's a point P, here's a direction V, here's my line. If I replaced V with the vector twice V, would it be the same physical line? Yes. V and 2V give same line. The equation of the line will look different. Time's going to be either running twice as fast or half as fast, depending on your point of view. It's the same physical object in space, but it will look different. What if I replace P and P minus 2V? Do they give the same line? If I change my base point, so here would be the point, say, P minus 2V. And now I want to go in the direction of V. Will that give the same line as going through P in the direction of V? So it's a good exercise. Go through the algebra. It's going to trace out the same points in space. The equation of the line will be different. Different times will correspond to different places. Will be the same line. And so if you think about it, if I look at the equation here, Q equals my base point P minus 2V plus T times V. Well, if I take T to be 2, that brings me back to here. If I take T to be 3, I come to here. It's going to sweep out the same physical object, but time will be parametrized differently. Now at time t equals 0, I'm not here, I'm over here. So I'm changing what I call my start time. Not a big deal. How many variables do you think we need to describe a plane? 3. I heard 3, I heard 2.
2.
So how many do we need to specify a line? 1. Once I tell you t, you know exactly where you are. You have your anchor point, you have your direction. A line is a one-dimensional object. A plane is a two-dimensional object. We start off in 3 dimensions. I need 3 numbers to specify where this chalk is. If I then confine my chalk to live on this blackboard, it's now in a 2-dimensional subspace. It's in a plane. I only need 2 numbers to specify. The third one is determined because it has to live in a plane. A line, I have 2 constraints. Okay, so what I want to do now is I want to talk about what should the equation of a plane be. Okay, so equation of plane. So given point P, and how many directions do you think I need? Yes?
2.
2 directions. And 2 directions V and W, the plane through P in these directions is all points Q, such that Q is P plus TV plus SW. Why do you think we use S? Yes?
Because if you used a U after the T, then it would look sort of like V.
So U could look like V. We often use U for U substitution and for other variables. Why do we use S?
Because it comes before T.
Yeah, it comes before T. I hate using S. S's often look like 5s. But I need 2 letters. Typically use S and T. let's draw what's going on. So if you think about this, this is a plane. If you lived in a city that had a understanding of how streets should be designed, what would your two directions be?
North and east.
North, south, east, west, right? Those would be good directions. You could be in a poorly designed city. You could be in a city where things are coming in at strange angles. If I give you something like this, well, I mean, it doesn't matter. Let's do something like this as my two directions. Here's V, here's W. It turns out as long as V and W are not in the same direction, that's perfectly fine, and it's going to give me a plane. And the reason is, I can use W first to get whatever height I need, and then I can correct, if I want it to be this point here, I can move over by using V. So in a linear algebra class, you'll do this in great generality. Really, once I have two directions, V and W, their combinations will span a plane. And so if you think about what's going on, here's my direction P. You give me some vector Q in this plane. I can look at P at Q minus P. And I want Q minus P to live in the plane. So Q minus P should be a combination of V and W. And that's where we get Q minus P is TV plus SW. Or Q is equal to P plus TV plus SW. What's the easiest combination of S and W of S and T to look at? Easiest choice of S and T. 0, 0. Alright, if I take 0, 0, I get the point P. What if I always take S to be 0? What do I get? A line. What if I always take T to be 0? A different line. And so the first one would give me this line in space, the next one would give me that one. This is going to give me, in some sense, a combination, what's swept out by those two lines. Spinning them in that plane. Okay? So if I give you two directions, you can form the plane. And so we would do the calculation exactly as before. I give you P, V, W. You write down the equations. Okay. So if we look at this, this is nice if I'm given V and W. Is there another way to be given a plane? Is there another way to look at a plane? Yes.
3 points.
So another way is if I give you 3 points determine a plane. So what you could do with the 3 points, use one of them as your anchor point, and then you can calculate two distances, like two vectors like this, and now you have your two directions, and now you can get your plane. So if I give you 3 points determine a plane. Yes?
You can determine plane cylindrically, like through cylindrical coordinates?
Those are special things. How do you mean by cylindrical?
I guess just through like a cylindrical coordinate system in which yeah, like a circle determines a plane.
Right now we don't have circles, so we'll use cylindrical coordinates later.
You could have a point on the plane, a line on the plane, and then a line normal to the plane.
So you actually don't even need the point, the line in the plane. So another way to determine a plane is it's all things going through a fixed point that are perpendicular to a fixed direction. So imagine I give you a vector P, and I give you a normal direction n. And I want to look at all vectors that are perpendicular to n. Well, how many directions are there? How many different directions are there? 3 directions in space. If I've given you one direction here, there's 2 directions that are left. So the things that are perpendicular to it will give you a 2-dimensional space. And so imagine I give you 2 vectors v and w. Do you know any way to get a direction perpendicular to the 2 of them? Yes?
Cross product.
The cross product. Right? So if I have 2 vectors, there's lots of things I can do. I can add them, I can subtract them. Right? Not really helpful. I can take the dot product. That gives me a number. You always want to know what kind of outputs do you get. I can also take the cross product. And so I can let n be v cross w. And if I do v cross w, this is perpendicular to v and w. And it's not going to matter if it's unit length or not. So this is going to be another great way to write down the equation of a plane. So what I can do now is the following. So given point P and normal direction n, the plane through P with normal n is all q such that q minus p is perpendicular to n. Do we know any way to tell if two vectors are perpendicular? Yes.
If their cross product is 0? Is that?
No. So if I take I and j, their cross product is k, and that's not 0.
The dot product is 0?
If their dot product is 0. So if I look at q minus p and dot that with n, now is that 0 the number or 0 the vector? 0 the number. The dot product returns a number, the cross product returns a vector. So if q minus p dotted with n is 0, then q minus p is perpendicular to n. Well, I can expand, and this is the same as q dot n equals p dot n, if I just bring things to the other side. So this is another way to get the equation of a plane. Okay? So if I start giving you some inputs, so for example, I'm going to tell you p is 1, 2, minus 1, and n is 3, 1, 2. I can calculate the equation of the plane. And I would just do q dotted with n is p dotted with n. Right, so xyz dotted with 3, 1, 2 is 1, 2, negative 1 dotted with 3, 1, 2. Right, so I get 3x plus y plus 2z equals 3 plus 2 minus 2 is 3. And so the equation of the plane would be 3x plus y plus 2z equals 3. People often like to write in terms of z. And so if you want to write in terms of z, this is the same as z is negative 3 halves x minus 1 half y plus 3. If you look at it like this, now it's clear. You give me two numbers. You give me two inputs, x and y. Did I make an algebra
Is
mistake?
it 3 over 2?
3 over 2, yes, thank you. You give me two inputs, x and y, and my third, z, is uniquely determined. This is another way of seeing it's a two-dimensional object. As a good exercise, what you should do is you should take a point P and take two vectors v and w and calculate the equation of the plane. Then take v cross w and use that to calculate the equation of the plane this way as well, and see that the two of them are the same. Do you want to replace v cross w with a unit vector in that direction? Do you want to divide by its length? Do you want to take sums of squares of components and take square roots? No, right? If I multiply the normal by 5, I change this side by 5, I change this side by 5. It doesn't have to be a unit vector. That's extremely convenient. So there's no need to normalize. There's no need to make sure your components are unit length. Okay? So these are equations of lines, these are equations of planes. These are going to be key building blocks for us for what comes on. Okay? Any questions on what we've done so far? Okay. There's a lot more examples in the video that's online. There's a lot more details in terms of the lecture notes that I've posted, in terms of what I'm going over. What I want to do is I want to free up some time in every class to try to motivate the material and see a bit more of what's going on. So we're going to do two parts. The first part is going to be a little bit of mathematics and art, and the second part is going to use binomial coefficients. So I want to just quickly review Pascal's triangle because I'll need that. And then after I do Pascal's triangle, I will then go and do the video. How many of you have seen Pascal's triangle? So this is the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. Okay? Each element is the sum of the two above it. And the rule is I just have strings of ones going along the diagonals. So the question is, why do we care about Pascal's triangle? If you expand x plus y squared, you get x squared plus 2xy plus y squared. If you expand x plus y cubed, you get x cubed plus 3x squared y plus 3xy squared plus y cubed. What you hopefully see is these coefficients are what you get when you expand these quantities. I claim you've either seen or should have seen these in a Calc 1 class. Except instead of using the letter y, they used a different letter. Anybody know what letter you used? When you're doing derivatives, what letter did you use instead of y? H, excellent. When we were trying to calculate what's the derivative of x squared, x cubed, x to the fourth, x plus h squared minus x squared divided by h. Take the limit as h goes to 0. Fortunately for calculus, all we really need for Pascal's triangle is just this column, this diagonal, and this diagonal. The other ones we don't really need if we're just taking the derivatives of these functions. These will turn out to be useful for many other things. But really all we need, fortunately, is just the first two diagonals. So in a few minutes we're going to play a game. And the game is the following. Whenever I have an odd number in Pascal's triangle, I'm going to fill it in. Whenever I have an even number, I'm going to erase it. So I will fill that in, fill that in, fill that in, fill that in, erase, fill that in, and I'll continue. Okay? And I'm going to draw a picture of what happens. When I draw the picture, rather than drawing it like this, it was more convenient for me when I was writing the computer program to draw it sideways. The reason is I'm plotting on the x-axis. And then this is going to tell me how many rows down I go. I'm going to always adjust my box so that I have an equilateral triangle. So if I have 20 rows, I will adjust it so that 20 goes to the point 1. If I have 50, I'll adjust it so 50 goes to 1. What I want to do is I want to keep drawing the Pascal's triangle when I shade it in, always in the same region. So you can see as I add more and more rows how it fills in. And hopefully you will enjoy the movie as it fills in. Okay? If not, my apologies, but best I can do. Okay? Everybody understand how we're going to draw the picture? Alright, so we're going to move the camera over. We'll use the screen. Alright, so we're going to start off with briefly lines. So I might have told you the solar wit story. Last year I was dragged to the art museum, Mass Mocha, with my kids. It was family day. And I was not happy, but put on a big smile. And Kayla made my day. She was 3, she goes, Daddy, Daddy, Daddy. What? Star Trek. It's not quite right, it should be curved, it shouldn't be symmetric. But solar wit is very famous for just drawing with lines, create a very good living. Right. This is one application of lines. Okay? If you can convince people to spend enough money, you can make a good amount of money. Here's a better one. How many people know about Thomas Eakins? He's now my favorite American painter. He may have had some interesting private life activities that somebody in the 10 a.m. section knew about, potentially. So I will phrase the question very carefully. Does anybody know what no-no artistically he might have done in his paintings? Not talking about personal life paintings. He did something that people considered cheating. So this is a picture of a couple of people on some kind of beach watching a boat. Many years after it was painted, somebody found in someone's attic a photograph of these 4 people on a New Jersey highway. Exact same 4 people, same clothes, same pose. What Eakins did is he used the technology of the time to project the photograph onto the canvas, and he put little dots in the canvas to get the perspectives right. And they investigated, and they actually found the dots in his work, not just here, but in other paintings as well. And he had it hidden from people. Now, as a mathematician, I love it. You know, why spend your time doing tedious calculations where you can get around it? You know, the way I do Sudokus is I wrote a computer program to do the algebra for me. And then just, you really go through and cross these things out. Let me get the interesting part. Eakins didn't want to spend time doing the boring stuff. It's a very simple geometry problem to project. And so he wrote, he didn't write a program. He just projected the stuff onward. And I believe some of his students also did this. But again, a lot of people feel that this is not appropriate for art. You're supposed to do it all by yourself. So, different people have different views as to how this should be. How many of you have ever seen the movie Tron, the original, not Tron Legacy? Alright, how many of you have seen Star Wars, the original? Alright, too many of my students have not seen Star Wars, so last semester we had Star Wars screenings. There will probably be a Tron screening. I think the original still holds up pretty well. But it's from, I think, the early 80s. The special effects are fairly primitive. It's one of the first computer animated movies in places. And essentially all the computer animation is, what did you guess? Lines. There's a few circles, but it's mostly lines. Okay? Computer animation is a huge application of these equations of lines and planes, figuring out where things are and projecting them. Getting the images and perspectives right. In the additional comments today, I will post a link to a nice paper by a colleague of mine from Smith. What they do is if you're given a photograph, they can figure out where the camera was. So if you want to see how has a building changed over 100 years, you know exactly where to put the camera, so you can take the picture exactly the same as before. Alright, what I want to do now is I want to end with, the movie I promised. Alright? So what I'm going to do is I'm going to draw Pascal's triangle. I'm going to always adjust it so I have an equilateral triangle. And so here I'm drawing just the first 3 rows. And as time passes, I'm going to add more and more rows. And the question is going to be, how do things fill in? How many of you think it's going to fill in as a one-dimensional shape? How many of you think the triangle is going to fill in as a two-dimensional shape? How many of you think it's going to fill in as a three-dimensional shape? So we're just doing things on the plane. So 3 dimensions is probably out. What other possibilities could there be? Shouldn't it be either 1, 2, or 3 dimensions? Right? Alright, so let's go again. How many people think it should be 1 dimension? We don't have that many choices, guys. You gotta vote. You gotta vote. 1 dimensions. 2 dimensions. 3 dimensions. Other. Alright. Here's the movie. Time is going very slowly. We'll speed up time a little bit. Speed up time a little bit more. You can start to see patterns emerging maybe. It's a little hard right now. Fractal. It's going to be a fractal. And so at this point, I keep adding another row and then I keep rescaling to keep it in the same size box. And so the question is, as time keeps passing, how much of the equilateral triangle will it fill in? We have 3 minutes left, so we're going to speed up time a little bit. Let's let time run faster. Alright, so now it's starting to look really cool. And that's a good place to stop. I think I stopped here 1 second short. There you go. That's the right place to stop. Notice the remarkable self-similarity. This region here is the same as the region here and here. This whole block here is the same as the whole block here and here. And of course, you can keep going smaller sizes. This is the same as these. Anybody here CS or potential CS? Anybody here just like to write programs? If you do like to write programs, this is a really good one to try to write as to how would you make a good movie with this. I sadly couldn't find one online, so this is a very short, easy program to write, but it's not going to allow me to go into too much detail. Do I need to get into too much detail? I mean, at some point there's going to be so many dots inside, it's going to be tough for us to just really distinguish what's going on with our eyes. So I can let time go a little bit faster now, and you can start to see how it's filling in. And so the question is going to be, what happens as you continue to allow time to evolve? And so there's going to be an incredible pattern of filled in and unfilled in. And in the limit, it's going to be something that's more than one dimension and less than two dimensions. It's going to be a fractal shape. And so how many of you are potential econ majors? If you're econ, you really want to learn about fractals. So a lot of people feel that the models used for the stock market, these standard Brownian motions, these standard coin tossing models, are not the right models to use. You really want to use a fractal model, and that does a phenomenal job of fitting price fluctuations. The reason it's not done is it's harder math and you have to wait for the old people to die off. You are not allowed to help them. Okay? That's frowned upon. But eventually people do die. And this is what happened in quantum mechanics. You had to wait for the old tool to die off, and then the new people were able to run with the subject. The real question is, what math do you know? When you know different math, you can do more and more things. Fractals are used for a huge number of things. I watched a very bad movie recently, Star Trek Into Darkness. I don't mind if this is recorded and posted. I don't like what they've done to the franchise. How many people have seen that? How many people have seen the original Star Trek Wrath of Khan? A much better movie. Wrath of Khan was the first example of using fractals in a movie. When they did the Genesis torpedoes for the special effects, it was fractals. A lot of great articles, what is the dimension of the coastline of Britain? And it's not an integer, it's a fractal number. Which do you think has a bigger dimension? The coastline of Britain or the coastline of Norway? Good question to end on. Yes?
Norway?
Why?
It has lots of fjords. And
Yeah, the fjords and stuff like that push the fractal dimension of Norway's coastline above that of England. Or Great Britain. So anyways, this is what I kind of want to do with the flipping of the classes. I want to try to show you a little bit where all this stuff is used and have time to keep this material motivated. Feel free to send me comments either directly from your email accounts, or if you want to log on and use Math150, please do that as well. All right.